Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman. In this video, we're going to go over SN1. Now at this point, we've covered most of the details. And as you'll see, this video is a lot shorter and a lot easier to go through, okay? Because all the tough stuff is done. We understand all the important details about nucleophiles and solvents and understand how to basically connect these molecules to make the products that we're looking to draw. Everything, all the heavy lifting is done. Now we just have to put together the SN1, understand what unique characteristics it has, fortunately not many, and then we'll move on to the comparison. We're going to learn about how to relate SN1 and SN2 together, and that's the last video of this series, okay? And that'll cover chapter 6. So let's get started. So the first thing we're going to do, just like we did with SN2, actually if you look closely, you'll see it's the same exact thing. We're going to do kinetics, the mechanism, factors, and then problems. So it's the same pattern, but a lot faster to go through it. So let's start with the kinetics. Now for an SN1 reaction, remember what I had mentioned that in the SN1 reaction, this is where a substitution takes place, but it doesn't happen at the exact same time that the leaving group leaves. First the leaving group leaves, then the substitution takes place. So we're doing this in a different, in a two-step process at different points in time. Okay, so the rate of an SN1 reaction is equal to the rate constant times the concentration of just the substrate. That's it, only the substrate. So this means that the nucleophile has no influence on the rate of this reaction. It doesn't speed it up, it doesn't slow it down. It has nothing to do with the rate, okay? That's what we're seeing here so far. Very important. Now, as far as the idea here is that, remember, this is unimolecular, and that means that the substrate is what's most important. So let's take a look now at the mechanism. Now, let's say we have, let's do an actual, I'm going to do a more concrete example since we've now seen all the stereochem and things related to it. So let's say we have a BR over here, and this is wedge. All right, and now I want to treat this with some sort of nucleophile. I'm going to write water. So water is actually acting as both a nucleophile, but it's also acting as the solvent. So it has two different roles here, the solution and the nucleophile. Now, when this happens, what takes place first, and by the way, let me put another group here. I want to make it tertiary. So now we have this tertiary system. And what I'll do is I'll put an H here. Actually, no, I'll put a methyl there, but we'll put a propyl here. P-R-O. Well, actually, no, I'm sorry. Let's make this an ethyl. So we have an ethyl, a propyl, and a methyl. Okay. Now, when this reacts, the first thing that happens is independent of the nucleophile, this is going to leave. And eventually you'll get to what's called a carbocation. So now this is ethyl and this is positive. Very important, this is positive. Now, right now, this right here is chiral, right? But what takes place first is that you make a carbocation. This is sp3 that becomes sp2. Now, a carbon that has only 3 bonds and positive is no longer sp3, it's sp2. So whatever chirality it had, it now lost. Because at this point, there is no chirality. It's a carbocation that lost its chirality. Now, in the next step, water comes in. Now, water is both the solution and the nucleophile. So water is going to come into this, and the question is, does it come in from below? Does it come in from above? And the answer is yes to both of them. Because there's no push, there's no displacement, this comes in on both sides. What we say is this has inversion and retention. That's the key thing here. So for an SN1 reaction, you get inversion. So if the BR is in the wedge, then the next thing coming in is in the back, but you also get retention. When the BR leaves, it's gone. So there's no reason why the water can't come in from the front. And so you wind up getting both. And so our answer now would be where water comes in this way, and then there's a ethyl in the back, or water comes in from the back, and then what would be on the front? Well, what was in the back? Ethyl. So now it's on the front. Ethyl's in the front. So you see that you get both answers here. You have inversion and retention. So this one here is retention, You have the same stereocenter that configuration. It's on the wedge the way BR was, but you have inversion as well, and you get both of them. Okay, so this is the mechanism. And finally, the last thing to do is actually to just stabilize that water. Notice how water came in, it's positive. So the last thing we do is we pull off an H from the water. And how we do that is, there's a few ways to show it, but I'll show it to you this way. I'll have another water just pull off those H's. So it just pulls off the H, and you wind up getting wedge OH, back ethyl, or you get back OH and wedge ethyl. So this is the mechanism. This is the full details. So let me go back from the beginning. The halogen leaves, the leaving group leaves, and nothing else happens until after it leaves. You get to this next part, carbocation forms. Once that forms, now the nucleophile comes in, separate step, and it can come in from the front or the back, so you get inversion and retention. But if the nucleophile that comes in is neutral, then it becomes positive. It loses an electron when it makes a bond, so you have to pull an H from it. And that's what we did down below. We pull off the H. This is the mechanism. And here's the energy profile for this mechanism. We start somewhere in energy. We wind up, of course, lower, always, right? So here's reactant and here's product. But we go through a transition. We go up a hill and we go to intermediate. That's I. And then from here, we drop down to the product. Now, the reality is that this has more than two steps. This has another step where we pull off the H. If you want to show that, sometimes they don't show it to you, but if we want to go through that step too, then we can just drop this down here and then drop again there. So this is I2, this is I1. What's most important here is this. When your first step, the first step is the first thing that happens, right? So that's when you pull off the BR and you make a carbocation. That is always the rate determining step. So this is what's called the slow step. That means it's the highest hill to climb. That's all you have to remember. The first step in an SN1 is the slow step. So this is going to be the one that has the highest hill. So here's my delta G double dagger, and it should be highest hill to climb. And so just to make that clear, let me just make it a little lower. So we can go like that, and there you have it. So that's what's most important. So the first step gives you intermediate 1, carbocation. And then after intermediate 1, carbocation, you go to the next step, you get intermediate 2, which is where you have the positive oxygen. But then you pull it off and you get to the end product. So I was counting the product as another I. And so there you go. So this is correct. So this is the cation. This is the OH2 plus, and then this is the alcohol product down below. So this is the energy profile that we're looking at here. Okay, and so there's a transition state 1 and transition state 2 and transition state 3. See that? So you have all that stuff as well. Okay, so this covers the mechanism and this covers the energy diagram. Okay, now what's important to note, again, is that the rate is only dependent on the substrate. So if I double, triple, quadruple the amount of water, it does nothing to the rate. But if I double or quadruple or triple or quadruple the substrate, it's going to make the reaction 2 times, 3 times, and 4 times faster. Right? So that's important to note. This is our substrate, and that's what's most important for this reaction. Okay. Now, what we're going to do next is we're going to go through the details just the same as we did with SN2. But what we're going to find is it's, like I said, a lot easier to go through. So the first one, A, let's talk about the substrate. Now, this one's actually an important one. Now, for the substrate, we are making a carbocation. This is extremely important. We make a carbocation. So we have to think about, notice that in this first step, it's an endothermic step. So going from R up to this first intermediate, it's very high in energy. It's closer to the top of the hill. So the carbocation is the most important characteristic because it's what influences the rate of the reaction. So because our first step looks like this, to make